Hello viewers, in today's lecture we will study about maxima and minima. Viewers, maxima and minima is an important application of derivatives. The concept of derivative of a function is very significant in finding the maxima and minima of a function. Now let us take a function y equal to fx. Let this function be continuous and differentiable in the closed interval a comma b. Now viewers, in maxima and minima, our main aim is to find out the turning points or the points where the graph of the function takes a turn. Clear? And such points are called turning points. Turning points or stationary points. Clear? Suppose we have a graph like this. Suppose we take a graph of a function y equal to fx, and we have the graph as, say, this is the graph. Clear? And say this is x, this is o, this is x prime, this is y, and this is y prime. Clear? And let this is a graph of this function y equal to fx, and let this function is defined in this closed interval. Clear? Okay. Now, what are turning points? Let us first understand the meaning of stationary points and turning points. Viewers, we see that this graph is at some intervals this graph is increasing, and at some places this graph is decreasing. Clear? So let us mark some points here and say this point is A, and say this point is B, and this point is C, this point is D, say this point is E, and this point is F. Clear? And so on. Now here we see that B, D and F are 3 points where if we draw the tangents, suppose if we draw the tangents, this is the point F. Clear? This is point F and this is point B. Clear? Now the points B, D and F are called the turning points, and because at these points the derivative of this function y becomes 0, or f prime of x is 0, or the slope is 0, slope of the tangent is 0, or the tangent is parallel to x-axis. Clear? So what are turning points? Turning points are the points where the derivative, the sign of the derivative changes. Clear? I will elaborate on that after some time. Let us first take the turning points. So turning points are the points where the graph starts increasing or decreasing. At this point, if we take this point D, then after the graph starts decreasing from this point D here, and if we take this point B, and from here the graph starts increasing, and from here it starts decreasing. Clear? So turning points are the points where the derivative is 0, or we can say the slope of the tangent is 0 or the tangent is parallel to x-axis. Turning points are also known as stationary points. Clear? So viewers, in maxima and minima, we have a function, we plot its graph and we try to find the turning points. Clear? The turning points are obtained by differentiating this function with respect to x and then putting the derivative equal to 0. So f prime of x equal to 0 is the equation which gives the turning points. If we solve this equation, f prime of x equal to 0, we'll have the roots, say x1, x2, x3 and so on. Clear? And these points constitutes the set of turning points or stationary points. Clear? Okay, now let us take the formal definition of maxima and minima. Now viewers, we have the definition here. Let f be a function defined on an interval I and the interval is from point A to point B. Then f is said to have a maximum value in I if there exists a point C in I such that f of C is greater than or equal to fx for all x belonging to I. Clear? So let us discuss it in detail. Suppose we have a function y equal to fx and this function is given in this interval a comma b and this is the interval I. Now suppose the graph of this function is, say we have this graph. Clear? Now here we see that this is x o x prime, this is y o y prime. Clear? Now here we see that, say this is a and this is b. Now f is said to have a maximum value in I. Maximum value. So we see that here this point is C. Clear? Now say this point is here, this point is A, and if we draw a tangent here, we see that this point A is a turning point. Turning point. Clear? This is the turning point. And we see that at this point A, this tangent T is parallel to x-axis. And here obviously the derivative of f is 0. Now let us come to this definition. Let f be a function. We have this function y equal to fx. Clear? It is defined on this interval I and f is said to have a maximum value in I if there exists a point C in I such that f of C. See, f of C is actually equal to AC. This length AC. Clear? It is this length AC is greater than or equal to all values of f of x for all x belonging to I. So what does it mean? Let us say this point is, say, x1 and say this point is x2. Now viewers, it is clear from the figure that that x1 and x2, both these points belong to this interval a comma b. C is obviously belongs to this interval AB. Now what is f of x1? See, f of x1 is obviously less than f of c. Clear? Similarly, f of x2 is less than f of c. If we take any other point, say here x3, and say here we have say x4, clear? Then we see from this figure that this green line AC is greater than all these blue dotted lines. Clear? So fx4 is obviously less than fc, and similarly f of x3 is less than fc. So for all x belonging to I, f of c, this is the greatest value. Clear? This is the greatest ordinate. So fc is the greatest ordinate for all the x belonging to this interval a comma b. Hence this ordinate AC is called the maxima. Clear? AC is the maximum value of this function, and AC is f of c. And this point x is equal to c is known as the point of, this is known as the point of maxima. Clear? This is the point of maxima. Clear? So this number f of c is called the maximum value of f in this interval I, and the point c is called a point of maximum value of f in I. Clear? So this is the formal definition of maxima. So here we see that A is the turning point, and from this point to this point the graph increases, and from after reaching the point A, this graph tends to decrease, and this point A becomes the turning point or the stationary point, and at this point the derivative is 0. Clear? This is to be remembered. So maxima and minima occurs whenever the derivative is equal to 0. So here the derivative is 0, and this point is a point of maxima. Point C is the point of maxima because fc is greater than or equal to fx for all x belonging to I. Clear? Similarly, if we take all these points, say this is x5, so f of x5 is again less than fc. So fc is the greatest value, and this constitutes the maximum value of f. Clear? Now let us take a similar definition of minima. Now viewers, here we have the definition of minima. Let f be the function. Again we have the function y equal to fx is defined on this interval a comma b. Then f is said to have a minimum value in I if there exists a point C in I such that f of c is less than or equal to. In the case of maxima, we saw that the equality sign, the inequality sign is reversed here. Okay, clear? So here we have f of c is less than or equal to fx for all x belonging to I. Clear? So let us take a graph here to understand the meaning of this definition. And here we have the coordinate axis, and suppose a graph is like this. Say this is the graph. Clear? Now here we see that that if this is A and if this is B, then this point, say this point is C. Clear? And if we draw a tangent here, see this is the tangent. Clear? This is the tangent line, and say this point is B. Now here we see that this point B is the turning point, See, from this point, say this point is A and this point is, say, C. Now as the graph approaches from A to B, it is of decreasing nature, and then after reaching this point B, the graph starts increasing towards this point C. So this point B is the turning point, and here this point C is known as the point of minimum. Clear? So what is the definition of minima? So minima says that f is said to have a minimum value in I if there exists a point C in I such that f of C is less than or equal to f of x for all x belonging to I. Clear? So let us take here 2 points. Say here if we have x1, say here we have x2. So here's x1, C, x2. All these belongs to this interval a comma b here, and we see that f of x1 is greater than f of C. Similarly, f of x2 is also greater than f of C. Similarly, if we take this point, this is x3, f of x3 is greater than f of C. If we take this point, say this point is x of 4, so f of x4 is also greater than fc. So this line segment or the ordinate BC is the shortest or minimum among all these ordinates fx1, fx2, fx3, fx4 and so on. So C is called, this point C, x equal to C is called the point of minima. Clear? And f of C is the minimum value of f. Clear? So here's this is the concept of maxima and minima. Clear? Now let us explain, or let us discuss some more things related to maxima and minima. Now viewers, let us consider this graph. Here we have a function, real function y equal to fx, which is defined in the interval, closed interval a comma b. Now viewers, here I am taking a function which is continuous and differentiable. Now let us analyze this graph. Viewers, I think if we analyze this graph, we can learn a lot of things about maxima and minima. Clear? Now here we see that the function decreases. The function decreases in from A to B. In AB part, the function decreases. Then from C to D, C to E. Clear? C to E, and then okay. Then we see that the function increases in the section BC and in the section EF. Clear? So this is the first observation. So here we'll have this graph and we'll analyze and we'll observe certain things from this graph. So the first thing is we have a graph of y equal to fx, which is defined in the interval I a comma b interval, and this graph increases in the sections or in the parts BC and EF. and it decreases in AB and CE. Clear? Now this is the first thing. Now the second thing is the turning points are or the stationary points are here we have B, and then we have C, then we have E. Okay, so here we have B, C and E as the turning points. Clear? Okay, now viewers, let us take the point B. Okay, now here we are taking, say, a point C. Clear? Now C belongs to this interval AB. Now let us take a point to the right of B and to the left of B. Say the point which is left of B is, say, this point, and the point which is to the right of B is, say, this point. Clear? Now say this point is C minus H, and this point is, say, C plus H. Clear? Now here this H is very small quantity, and it has its own significance, and H is very small quantity, and moreover H is greater than 0. So therefore we have a small interval here. We have created a small interval here which is C minus H and C plus H. Clear? So viewers, now we are analyzing this graph, and we have taken one of the turning points, and we are taking one point to the right and one point to the left, and the left one is C minus H and the right one is C plus H, and thus we have created an interval, say I prime. Clear? Now say this point is A, B, C, D, E, F. Say this point is G, and this point is, say, H. Clear? Now at point G, what we find? If we draw a tangent to this point G, and if we draw a tangent at the point H, what we will see? We'll observe that, see, this is the tangent. Okay, this is the tangent at point G, and this is the tangent at H. Okay, this is the tangent at H. Now we see that at point G, this tangent which is represented by this red dotted line has negative slope. See, the tangent is like this. See, the tangent is like this, and this is the x-axis. This is the x-axis, and the tangent is like this, and we have the slope as m equal to tan theta, and theta is obtuse here, obtuse angle. Clear? And if we observe this tangent at point H, we see that this tangent is like this, and this is the x-axis, and this angle is theta here. Okay, So m is tan theta, and theta is acute, and theta is acute. So now summarize what we have discussed so far. Now we have a point C here. We are taking a point C minus H, which is very close to C. Similarly, we are taking a point C plus H, which is very close to C. And then we are drawing tangents at this point G and H, clear, which are in the neighborhood of, neighborhood of. This is called neighborhood, clear. So we have drawn these two tangents, one tangent to the left and one tangent to the right, clear, and B is the turning point. So we have two tangents, clear, and in the neighborhood of this turning point B. Now we see that here this angle theta, this angle is theta, and theta is obtuse. So the slope of, or we say that the derivative dy over dx at this point G is negative, clear, and at point H we have this this tangent, the green tangent here. So the derivative is positive, clear. I hope it is clear, because at point G the tangent is making an angle theta which is obtuse, and this obtuse angle lies in second quadrant, and in second quadrant tan theta is negative. And what is tan theta? Tan theta is the slope, which is equal to dy over dx. So dy by dx at point G is negative, and at point H we see that the tangent is making an angle, acute angle, and this acute angle is lies in first quadrant, and in first quadrant tan theta is positive, and so our slope is positive, clear. So here's what we have concluded from this discussion. So we concluded that when the sign of the derivative changes from negative to positive, see, negative to positive, and B is the turning point, and here the graph first decreases from A to B and then increases from B to C, clear, and B is the turning point. So when such a situation arises and the slope or the derivative changes sign from negative to positive, then such a turning point B is known as a point of minima, a point of minima, clear. I am repeating it once again. See the structure of the graph. From point A to B, the graph decreases smoothly, then it increases. After arriving or reaching this point B, the graph starts increasing, clear. So B becomes the stationary point or the turning point. Here the tangent is parallel to x-axis, as we have discussed in while defining the turning point. So here the tangent is drawn like this. See, this is the tangent. Now we take a point, immediate point to the left and to the right of this point B. Now we draw two tangents. Why we are drawing two tangents? Because we want to find the slope, or we want to find the derivative. Now when we draw the tangent at point G, which is to the left of B, then we see that this derivative is negative. Why? Because theta is obtuse. Clear? Now if we draw the tangent at point H, the slope is positive, dy over dx is positive. So what we have seen here, when point B is a point of minima, then the derivative changes sign from negative to positive. And as a rule we can say that, or as a theorem we can say that, whenever the derivative changes sign from negative to positive, the turning point is known as a point of minima. Clear? Okay, now let us take this turning point C. So first we have taken this one, because here the graph is first decreasing and then increasing. Now we are taking this point C, because here first the graph is increasing and then decreasing. Okay, so now let us discuss this point C, because this point C is going to be the point of maxima. Clear? Now viewers, let us take this point P. In our just we have discussed that this point B is a turning point, and we declared that this point B is a point of minima. Now we'll take this point C. Clear? Now let us take this point C and take this point as small c. Clear? This is capital C, this is small c. Now take 2 points immediate to the left and to the right of this point C. Clear? So let us take the 2 points. So I am taking it here. Here's this is, say this is point C minus H, and here I am taking this is C plus H. So the discussion or the explanation is same as we have just discussed, and again we have created an interval here, and the interval is C minus H and C plus H, and H is a very small quantity, but it is greater than 0. Now see here we have these points C, and to the left of this point C, say this point is G, and here we are taking the point as H, as we have done in the case of minima. Clear? Now we will draw tangents to these points G and H. Okay, now let us draw the tangent. Now I am drawing the tangent at this point G. Okay, so this is the tangent. Clear? So viewers, this is the tangent at this point G. So this is the tangent. Now we see that this angle is theta, and theta is acute because theta is less than pi by 2. Theta is greater than 0 here, but less than pi by 2. So theta is acute, so m equal to tan theta is positive. Therefore the derivative dy over dx, clear? The derivative dy over dx at point G. What is derivative? Derivative is the slope of the tangent at any point on the curve. So here the point is G, and we have drawn a tangent at G, which is denoted by the red dotted line, and this theta is positive. Therefore m is positive, so is dy over dx. So dy over dx at G is positive. Now we will draw the tangent at point H. Clear? So we draw the tangent here. So viewers, this is the tangent. Okay, so this is the tangent at point H, and we see that this angle is now theta, and theta is obtuse and it lies in second quadrant. Theta lies in second quadrant, so m is negative because m is tan theta and tan theta is negative in second quadrant. So dy over dx at point H is negative. So what we have concluded, this point C is a point of maxima. This is a point of maxima, and at C, the C is the turning point here, and the tangent at C is parallel to x-axis. So what we have observed, when we have a point of maxima as the point C is, then the derivative changes sign from positive to negative. And when the derivative changes sign from positive to negative, then the turning point is known as a point of maxima. Clear? So here we saw that the tangent was like this, one tangent was like this, the other was like this. So the sign of the slope changes from negative to positive in case of minima, and in case of maxima the sign of the derivative changes from positive to negative, and this is known as the first derivative test for maxima and minima. Clear? So viewers, I am once again recapitulating this discussion here, and we will see what do we mean by the first derivative test. First derivative test. Suppose we have a function y equal to fx, which is defined in an interval a comma b. Now we are interested in finding out whether this the points we are interested in finding out the points where the function attains maxima or minima. Clear? So what we will do, in case if we apply the first derivative test, we will see that if the derivative, first what we will do, we will find the turning points. First we will find the turning points. Find turning points, and then say the turning points are obtained by solving this equation. The derivative is 0, so we will solve this equation and we will get the turning points. The turning points are, say, x1, x2, x3 and so on. Then we will take the first turning point x1, x equal to x1, and then we will see whether the derivative, that is dy over dx, changes sign from negative to positive or positive to negative. So if it is positive to negative at x equal to x1, then x equal to x1, if this happens, if the derivative changes sign from positive to negative, then x equal to x1 is a point of maxima. And if the derivative changes sign from negative to positive, then x equal to x1 is a point of minima. Okay, so viewers, this is how we apply the first derivative test, and first derivative test is a very important tool for determining whether a point is a point of maxima or minima. Clear? So let us discuss some more things. So viewers, now I am summarizing the first derivative test. Suppose we have the function y equal to fx, and say if its graph is like this, and if we have a function y equal to fx, and if its graph is say like this, then what we have discussed so far, if this is the point C, then we take one point here, one point here, this point is C minus h, this point is C plus h. Similarly, what we do here, this is the point C, we take one point here, we take one point here, this is C minus h, this is C plus h. Now we see that when we draw tangent at this point and we draw the tangent at this point, we see that the slope of this tangent is positive, and the slope of this tangent is negative. And here also, if the function is first increasing, then attaining a stationary point, and then starts decreasing. So if we draw a tangent at here, the slope is negative, and if we draw the tangent at this point, then the slope is positive. So here we have maxima, and here we have minima. So this point C is a point of maxima when the derivative changes sign from plus to minus, and this point C is a point of minima when the derivative changes sign from minus to or negative to positive. Okay, so this is the first derivative test. Now let us solve some problems. Now viewers, let us take this problem, find all points of local maxima and local minima of the function f given by f of x equal to x cube minus 3x plus 3. So viewers, here we have two important terms, new terms, local maxima and local minima. Now before solving this problem, let me clear you this the concept of local maxima and local minima. Viewers, suppose we have a graph y equal to fx function. We have this function, and suppose this function is defined in this interval a comma b, and we have the plot of this graph here, and we see that there are some high points and some low points. So the low points are see, these are the low points, these are the low points. Okay, so what are the low points? We have say this point is say A, this point is say B, this point is C, this point is D. So A, B, C and D are the minimum points. Clear? And the high points are we have a high point, say F, here we have G, here we have H, and then we have I. Okay, I am not taking okay, if we can take this also. So we have say G, H, I, J. Clear? Now we have, this is a rough sketch, okay, and this is F, G, H, I and J. Now we see that here we have these points are known as the points of minima. Okay, minima, and these points are known as the points of maxima, and these points A, B, C, D are known as the points of minima. Clear? So A, B, C, D are the points of minima, and F, G, H, I, J are the points of maxima. Now if we select, or if we take the greatest, we can say the greatest maxima, then what is the greatest maxima? I think G is the greatest maxima. See, this is the maximum value of the function. So this point G is then known as absolute maximum, absolute maximum, or this point G is called global maxima, global maxima. Okay, and we see that here the points of minima are A, B, C, and D. And what is the lowest value? The lowest value is this value. I think this is the lowest value. Clear? So this point C is known as the absolute minimum. This is called absolute minimum, or this is called global minimum. This is called global minimum. This is called global minimum. So this point G is the absolute maximum or global maxima, or the greatest value. We can also write greatest value also. And the point C is called the absolute minimum or global minimum, or the least value, least value. Clear? So if this function y equal to fx is defined here in the interval a comma b, then G and C are called respectively absolute maximum and absolute minimum. Now what about the other points? So here's now the points F, H, I, and J. F, H, I, and J are called local maxima. These are called local maxima. And the points A, B, and D, the points A, B, and D are called local minima. Clear? So we have A, B, C, D, 4 points of minima, and out of these 4 points, C is the absolute minimum. So C is known as global minimum or the least value, and A, B, D are called the point of or the points of local minima. Clear? Similarly, F, G, H, I, J are the points of maxima, and out of these 5 points here, G is called the absolute maximum or the global maxima or the greatest value, and the other points F, H, I, J are called the points of local maxima. So I hope the concept of absolute maximum, absolute minimum, local maxima, and local minima are clear to you. Okay, so let us come to our main problem, which is written here. Find all points of local maxima and local minima of the function f given by f of x equal to x cube minus 3x plus 3. Okay, now viewers, let us start this problem. Now first what we will do, we'll find the derivative. The derivative is 3x square minus 3, clear, which can be written as 3x square minus 1, and we can write 3x minus 1 and x plus 1, clear. Now the turning points or the stationary points are given by f dash x equal to 0 or dy over dx equal to 0, because at turning point either we have the curve like this, the shape of the curve like this, or like this, clear. So these are the turning points. So f prime of x equal to 0, so we have 3 times x minus 1, x plus 1 equal to 0, so we have x equal to 1 and minus 1. So we have two turning points here.